All right, or Gen Chem, not Honors Chem, Gen Chem, sorry. Gen Chem, we are going to learn about strong acids and bases today, and we are also going to start introducing pH and how pH works as well. Okay, so let's start in with strong acids and bases. Now, acids and bases that are strong, that ionize 100% of the time, are called strong. And by strong, this is what I mean. If I had an acid that has hydrogens, when I put that into water, I would create hydrogen ions, and then whatever that hydrogen would be a negative ion, and that would also be in water. That little AQ, if you remember, reminds us that it's dissolved in water. So when I put strong acids in water, the hydrogens come off and create hydrogen ions, and the nonmetal or the polyatomic negative ion is also an ion, and they're free floating in the water. Okay? If I did this with a base, remember bases have hydroxide ions, the OH ions. If I put them into water, I would have the metal base ion, and I would have the hydroxide ion separated from each other, free floating in the water. So strong acids and strong bases, when I dissolve them in water, they separate to make their ions. So they ionize 100% of the time. That's what makes them strong. Okay, there are actually 7 strong acids. So let's get into those really quick. Okay, those strong acids are, there's 3 binary ones. There's hydrochloric acid, and that's me not writing well. Sorry. There's hydrochloric acid, hydroiodic acid, hydrobromic acid. Those are the 3 binary 2-element acids. Now there are 4 ternary ones that actually have the 8 or the ite that go to ic or us. So we have HNO3, nitric acid. We have HClO4. This is perchloric acid. We have HClO3. This is chloric acid. And then we have H2SO4, which is sulfuric acid. All of these are strong. Those hydrogens will dissociate 100% of the time and create hydrogen ions and then the negative ions in solution. Okay? There are 8 strong bases. Okay? So we basically have our group 1 metals. Now, if you remember group 1, they're the first column in the periodic table. So if I think of the group 1 metals, that very first column in the periodic table, I would have lithium, I would have sodium, potassium, rubidium, and cesium. Now, we don't include hydrogen because it's not a metal, and we don't really include francium because, let's be honest, francium is so radioactive that the half-life on that is only 22 minutes, so it's not stable. Okay, so these all will have a positive 1 charge. So that means we have to put 1 hydroxide group with them. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. All of those will dissolve in solution really readily to create metal positive ions and then the hydroxide negative ions and dissociate and ionize 100%. Okay, and we have 3 that are in the group 2. Not all group 2 metals will do this. Just 3. And the 3 that will do this are calcium, strontium, and barium. Now, if you remember, group 2 has a positive 2 charge. So that means to balance that charge out with a negative 1 charged hydroxide, I'm going to need to put 2 hydroxides on here. So calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay? Now remember, when we need to multiply a polyatomic or a group of atoms, we always put parentheses around that group and put the subscript afterwards to multiply it. That's why I have it written that way. So these are the strong bases and the strong acids. They will dissociate or ionize. So if I have this, it will dissociate into this. And if I have the bases, I will have a base and it will ionize and dissociate to give me the base and the hydroxides 100% of the time when they are strong. Okay? So, moving on. All other acids and bases are considered weak because they do not ionize 100% of the time. They actually stick together. So, instead of breaking apart into their ions, they actually stick together. As a result, they don't make very many hydrogen or hydroxides. Okay, because they stick together. They don't create a lot of ions when they're dissolved. Okay, so this is the trick. Because the list of acids and bases is so incredibly long, there's no way that you could memorize all the weak acids and all the weak bases. So it is so much easier to memorize the strong acids and the strong bases because then you know everything else is weak. And that's the easiest way to do it. So I would suggest that you make some flashcards of these strong acids and these strong bases and learn them. Okay? So it's flashcard time. Or you can make a Quizlet too, if you wanted to make a Quizlet. Okay, so let's draw a little picture of how a strong acid versus a weak acid would look in solution. And we're just going to use a generic HA for an acid. Okay, so we're going to use HA for our generic acid. Okay, so if it was strong, let's do strong here. And let's do weak here. If it's strong, it's going to dissociate. Let's put 5 in here. So if it's strong, I'm going to have hydrogens off by themselves in this solution. And then the nonmetal part is just going to be off by themselves in solution as well. Nothing's going to be attached to anything else. They're all going to be individual ions floating around in that water solution. Okay? That's what strong means. We ionize 100%. Okay? Weak. We do not ionize 100%. And so these are going to still be stuck together. We don't 100% ionize. So we're going to once again use our generic acid where we have the hydrogen bound to some negative ion. Out of 5 of them, maybe one of them would be dissociated or ionized. Now, in reality, weak acids, it's maybe 100 or even less to 1, 10,000 to 1, 1,000,000 to 1. Okay, those are really weak acids. So remember, strong acids create lots of hydrogen. So let's highlight the hydrogen ions really quick. And let's change this color so that so if we look at this, we've got a hydrogen here, we've got a hydrogen here, we've got one here, we've got one here. and we've got one here. So we've got 5 hydrogens in solution. When we look at the weak acid, we only have 1. So does that now make more sense why we call strong acids strong and weak acids weak? Okay, which one has more hydrogen ions in it? The strong one does, because the acid dissociates and we actually create hydrogen ions. Okay, we're going to do the same thing with a weak base and a strong base. So let's put the strong one here. And we're going to use our generic base, BOH, and we're going to put a weak one here. And we're also going to use a generic. Now remember, strong means that it dissociates 100% of the time. So that means I'm going to have these all over the place. Let's see. Okay, they're going to be individual ions floating around, but in a weak, they're going to stick together. So I'm going to have a bunch that are stuck together. And one that is apart. So let's highlight the OHs really quick. So if I highlight the OHs, I've got 1 here, 2, 3, 4, 5. I've got a lot. If I highlight the OHs here, I only have 1. So which one has more OHs? The strong. Because that strong base dissociates completely and gives us a lot of OHs in solution. Okay, let's go over the pH scale really quick. Now the pH scale is basically a logarithmic scale. And logs are, there's 2 types of logs. There's LOG, which is a log base 10. And then there's LN, which is a natural log. And you should see both of those numbers on your calculator. For the pH scale, we are going to use LOG. We're going to use log base 10. Okay? So let's do this little exercise really quick. The pH scale is a mathematical scale that's used to help us to determine the acidity, or sometimes the basicity or alkali nature. So the British call it the alkali. We here in America call it basic or basicity of a solution. It ranges from 0 all the way up to 14. 14 is the max. Yes, it is possible to have negative numbers and numbers higher than 14 on the scale, but it's super rare and it's beyond the scope of this class. Okay, so let's start trying to figure out logarithms. Okay, the first thing I want you to do is take these numbers, these 0.1s, 0.01, 0.001, and put it into scientific notation. Okay, now if you remember, anything where we had to move the decimal to the right was a negative. So these are all going to be 10 to the negative something. And however many spaces we have to move our decimal point to get the 1 to the ones place is the power of 10. So for example, right here, I would have to move my decimal place 1 space to the right. So this would be 10 to the negative 1 because I moved it 1 space to the right. Here, I've got 1, 2, where I have to move it. So it's 2 spaces to the right. So this would be 10 to the negative 2. Okay, so I want you to really quickly go in and put this in scientific notation really quick. Pause the video and let's check in just a minute. Okay, you ready to check your scientific notation? Okay, so this I had to move 1, 2, 3, so 10 to the negative 3. Okay, 1, 2, 3, 4, so 10 to the negative 4. Let's see, 1, 2, 3, 4, 5, 10 to the negative 5. 1, 2, 3, 4, 5, 6. Hopefully you see a pattern here. So 1, 2, 3, 4, 5, 6, 7, 10 to the negative 7. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 10 to the negative 9. 10 to the negative 10. 10 to the negative 11. 10 to the negative 12. 10 to the negative 13, and 10 to the negative 14. Okay, did you get that? Okay, so I want you to grab your calculator really quick and look around until you see your LOG number. Okay, I want you to take the log of each of these numbers. So let's take the log of 0.1. So a lot of these calculators, you're going to have to press the log button first, and then it will give you, let's see, it will give you a parentheses to put the number in there. So we're going to put the 0.1 in those parentheses, and we're going to close the parentheses as such. Did you guys see that? Okay, and then we're going to press enter. So that gives us a log of -1. And I'm going to put this in a different color so that we can keep this straight. So our logs are going to be in green, and our orange is going to be the scientific notation. Okay, so our log for this first one is going to be -1. Oops, and I needed to put that back into green. That was my mistake. So let's make that green. Okay, let's do that so press log and press 0.01, close the parentheses, we'll get a log of -2. Do you guys see that? Okay, so pause this, give yourself a minute, take the logs of all of these. So this should be -3. Is that what you got? And -4. Do you guys see a pattern so far? Do you see that the log is the power of 10? Because really, that's all a log base 10 is. It's just showing you how big or small that number is in terms of a base 10. Okay, so our log here is going to be -5, -6, -7, -8, -9, -10, -11, -12, -13, -14. Okay? Now, if we try and do a pH is a negative log. So I don't want to insert. So pH is the negative log of a number. So let's take the negative log, and we're going to do this in pink. Okay, so if I take the negative, so you're going to have to press the negative button first, and then hit log and put 0.1, and then hit enter, and you will get +1. Okay, and wow, this is really having a hard time thinking about all the stuff that we've written down. All right, so we're going to put come on. I'm sorry. I just want to change my color to pink. Okay, it's going to let me. I'm going to do pink. Okay, so we're going to do the negative log in pink. So if I do the negative log of this first one, I get 1. Okay, so let's do the negative log of 0.01. So press negative log 0.01, close parentheses, and you will get 2 and 3. And if you notice, we're just getting the positive value of the log that we just got. So this would be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay? So when we do the pH is equal to the negative log of the hydrogen ion concentration. Now these square brackets mean molar, which means moles over liters. And we've done moles over liters. Okay, so we know that it's a concentration, how many moles there are in a liter. Okay, so when we talk about a pH of 14, for example, let's highlight this really quick. If I talk about a pH of 14, that means my hydrogen ion concentration is 0.00000, like 13 zeros with a 1 after it. That means my concentration of hydrogen ions in that solution is very, very small. But if my pH is 1, that means my concentration of hydrogen ions is 0.1 moles per liter. So the pH just tells us how concentrated that hydrogen ion concentration is in that solution that we're measuring it. Okay? So, which of the above here is the biggest number that we calculated with our negative log? Okay? So our biggest number of the actual raw numbers was the 0.1, right? That is our largest number. It had a pH of 1. Did it not? Because it's the negative log. Which one has the smallest pH? That number, right? 0.1 had the pH of 1. So the smaller the pH, the more acidic it is. So the lower the pH, the more acidic. Okay, the higher the pH, the less acidic. The smaller that ion concentration is of hydrogen. So on the pH scale, 7 is considered neutral. So this right here in the middle of 7 would be considered neutral. Let's highlight 7. So this is neutral. So this is where the hydrogen ion concentration and the hydroxide ion concentration are equal to each other. So the hydrogen ion is equal to the hydroxide ion concentration. That is pH 7. That is neutral. Okay? So on a pH scale, 7 is neutral. Anything higher than 7 is considered basic. Okay? And if you're talking British English, they'll call it alkaline. Anything lower than 7 is considered acidic. Okay, so 7's neutral. Anything above 7 is going to be basic. Anything lower than 7 is going to be acidic. Okay, so let's look at this pH scale. Here's a pH scale with a couple of different things on here. We have our scale going from 0 all the way up to 14. Okay, so we have hydrochloric acid all the way up to sodium hydroxide, hydrochloric acid at 0 and sodium hydroxide at 14. Notice things that are 7 are neutral things: pure water, milk, human saliva, blood. Okay, we have things on the weakly acidic end, which would be like 5s and 6s, tomatoes, bananas, coffee, bread, salmon, potatoes. Normal rain is slightly acidic. Okay, then we get things that are mildly acidic: orange juice, acidic soil, soda vinegar. Have you ever tasted pure vinegar? It's pretty sour, right? Lemons, sour. That sour taste tells you it's acidic. Then we get into pretty strong acids or concentrated acids, battery acid, normal stomach acid. If you've ever thrown up and you had that sour, nasty taste in your mouth afterwards, that's because your stomach acid is pretty acidic. It's pretty strong. Okay. And then on the basic end, we have mildly basic things like seawater. Normal ocean water is about 8.2. Eggs are there. Baking soda, phosphated detergents, things that we use to clean. And then we get a little bit stronger bases. We have borax. If you've ever had that powdered soap in old-fashioned dispensers, and acids, those make your skin feel really slippery because it's dissolving a lot of your skin. Milk of magnesia, those are pretty decently strong bases. Then we get to really strong bases that are very basic. Ammonia, non-phosphated detergents like our dishwasher detergent, laundry detergent, and even detergent like dish detergent instead of our dishwasher detergent. Those are pretty strong bases, and that's why they're pretty hard on our skin. Bleach is a very, very strong base. Okay, and then sodium hydroxide, which is what we use as drain cleaner. Anytime you use Drano or Liquid Plumber, that's mostly sodium hydroxide. It's probably one of the most dangerous things you have in your house, honestly. Okay, so that's what the pH scale is. Next time we are going to look at actually measuring pH with a simulation and learning how to calculate pHs. Okay, so we'll see you next time. Okay, bye.